circulating the sign-up sheet. Okay, you start from here. Make sure you sign before you leave. We're about to start in 5, 4, 3. Okay, don't do this. Last time we talked about hydrate, right? We talked about gas contract and a little bit on hydrate. So today we will talk more on hydrate and have some calculation. And I did something for you, which is homework. Okay? Homework. You write something, 300 words is not that much. Okay, this is about the academic integrity. Second one is about code of ethics for engineer, so that we comply with ABET. Okay? And then we have gas revenue contract, percent of proceed, and some may say about near-miss experience or safety related. Just 50 to 100 words, very short. Okay. Fill in the blank. It's very easy question, but for part 2, you get -1 if answer is wrong when choices are provided. Let's test. Okay. 2.9. Oh, 2.8. Gas hydrate can form at the temperature higher than 32 F.
False.
True or false? True, right? Very easy, right? H2S at the concentration of 10 something can cause unpleasant odor and it is safe for 8 hours exposure. What's the unit here? ppm. Okay. Then maybe this too easy, but just do it, okay? So in the exam, it will be closed book. Okay? And the equation doesn't need to be this equation. It can be something else. Today we will talk more about hydrate. What's that about? And some calculation on flow through a choke. Then if we have more time, we can talk about line heater calculation and have some picture to show you. Line heater, and I think we may not have enough time to select the hydrate. Let's see, it's over there. Where's the sign-up sheet? You're signing it, right? Okay, keep doing it. And the camera is on the top. Question before we start. Okay. Oh, lab session. How many sessions that you enroll for labs? The first one I think is like 1 to 4 p.m., right? Is it? And second one is 4 to something p.m. Who is in the first lab session? Second one. Okay, so second session, we don't have any problem. But for first session, we may have to split. The actual lab will be from 1 to 150. That's first group. And then 2 to 250, second group. And the last group will be 4 to 450. Next lab is next Wednesday about the separator. Okay. Let's talk more on hydrate. I showed you this slide last time, right? And this one. So hydrate form at high pressure, low temperature. Okay. When it's cold and it's a lot of pressure. This slide gives you MPa. What is M for? What is M? London breathing.
1,000 Pascal.
I disagree. Stuart W. Bruce. Where's Stuart? What is MPa? Mega. Okay. It's really tricky, right? If you have M SCF, that's 1,000. But for MPa is megapascal, million pascal. Okay, don't miss this. That's for M. Okay. The next graph The previous one is a theoretical prediction for the case where we have just methane, nothing else. Ethane, nothing else. Propane, nothing else. Of course, you need water, right? The next one is we have pure methane, and I identified it as gravity of the gas. 0.6 gas gravity, 0.7, 0.8, 0.9, 1.0 gravity of gas. Brian J. DUHRKUHL. Yes.
That's me.
How do you calculate gas gravity based on molecular weight of gas?
It's over air, like
20 something? 29?
29.
29. Yes. So we need to know the air molecular weight, right? The molecular weight of gas divided by molecular weight of air, then we know the gravity of gas. Then we will know which line to use. So let's say we do the calculation and we get 0.7. So that is hydrate phase envelope. Okay. And that's a good approximation for natural gas. However, the accuracy become not quite good when we have something else. N2, CO2, H2S. So something else that is not combustible, it makes this prediction of hydrate phase envelope to not be that accurate, but it's still okay. Please be aware of that. And this is a conversion, 1 psi to Pascal and 1 megapascal to psi. Psi that we use here, or pressure that we use here, is absolute pressure, okay, not gauge pressure. This graph is the same as the previous one, but the unit is psia. Maybe this time is easier, right? psia. And we have temperature. So if I have temperature of 50 and gas gravity of 0.6, I can, if my pressure is like 600 psia, I can form hydrate. Right? So it doesn't need to be below 32 Fahrenheit. Above 32 Fahrenheit, we can form hydrate. And how do we prevent it? Method 1, we remove water. We put inhibitor in. Inhibitor can be methanol, or we can avoid the operation inside the hydrate phase envelope. Okay? So we try to, but that's not always possible, right? So if we have pressure and temperature within the phase envelope, we cannot move it out, right? So the pressure from the reservoir, it will be hot. So we have reservoir hot gas coming up, but at the surface during the winter it can be cold. When it's cold, the temperature inside the pipe, the outside may be, let's say we have a buried pipe. The pipe is buried underground. So outside we may have ice, but temperature over there may be like 40 Fahrenheit. No ice forming. But even 40 Fahrenheit with the buried pipe, we may have hydrate if pressure is high enough. Okay? If pressure is high enough. So hydrate formation should be avoided. Hydrate do not dissociate at the same condition with when they are created. This means if we enter the hydrate phase envelope over here, this point, and the temperature go down, pressure maybe stay the same, and we form hydrate in this part. When we increase the temperature, it doesn't mean that hydrate start to melt at that point or melt completely at that point. Okay, so the temperature that hydrate may melt completely a little bit outside the phase envelope. Okay, so we should avoid hydrate. We have the equipment to heat it up, heat gas up so that hydrate won't form when it's cold. Even though we have hot gas, gas temperature can drop a lot if we choke it. You agree? If I have flow through a choke, pressure drop a lot and also temperature drop a lot. JT cooling, right? Joule-Thomson cooling. So even though you don't have hydrate to begin with, the gas is hot, but when it go through the choke, pressure drop a lot, then we have Joule-Thomson cooling. Then the temperature can be within the hydrate phase envelope. How do we prevent that? So if we know that we choke, then it will be too cold and it will form hydrate. This means we have to heat it before we choke. Make sense? So we heat it before we choke. The equipment to heat it is line heater. How do I want to heat my natural gas? Do I put natural gas to open flame? I don't do that, right? It will have combustion, maybe explosion or something. Do I put a coil that is very hot, heat it with the electricity? So gas flow in and we have a hot coil. Do you like that idea? It's too hot, right? So the coil, we may create fire. It's too hot. So the method that we use conventionally is to heat water first and use hot water to heat gas. That is safer, right? We don't have gas contact directly with a very, very hot element. Okay? Last year and 2 years before, and maybe 3 years before, we had the question on this part. Line heater, is that indirect heating or direct heating? And some of them, maybe 10%, 20% of the class get -1 or something. Don't be that person, okay? So we heat the gas stream before, and we can also heat before and after the show. We have 2 different types of line heater. I will show you shortly. Other than line heater, we can use LTX unit, low temperature exchanger. Use the high flowing temperature of the well stream to melt the hydrate after they form. So with LTX, we let it form first, then we melt it. Okay, that's LTX. LTX is more expensive than line heater in general, so people mostly use line heater. Okay. How do we know how much should we heat? How many degree Fahrenheit should we heat the gas stream? We don't know, right? Unless we know what will happen if it flows through a choke. Make sense? So if I know that after it flows through a choke, temperature will drop by, so when it comes, let's say 80 Fahrenheit, go through a choke, temperature drop to 40 Fahrenheit. But I know that hydrate form at 50 Fahrenheit. What do I do? What do you suggest? Any suggestion from Richard M. Bumate? Hello, Richard. What's your suggestion? I have gas coming in at 80. When it flows through a choke, temperature will drop to 40. And I know that hydrate will form at 50. I should heat the gas instead of 80. I should make it hotter, right?
Yeah.
To what temperature? Roughly. 81, will that be enough?
No.
So, Richard,
Yeah.
what do you want me to do? If not 81, 82? Still wrong, right?
Yeah,
83. What temperature should I heat this up?
120,
100?
120?
Oh, you want it to be very, very hot, right?
Yeah.
Too hot is not good. Okay, and if we have it too hot, number one, it won't form hydrate. Let's say we heat it to 120. It goes through the choke, it won't form hydrate, right? And temperature may drop another 40 Fahrenheit and become 80. It won't form hydrate. The problem is we spend too much money on the energy to heat it. Make sense? So maybe we heat just to 92 or 95 or something. Okay, not too much energy. So above it and a little bit more as per the safety factor of your company, so that we add just enough energy and a little bit more so that it doesn't form hydrate. We don't pay too much to heat the gas. Okay? Alright. One thing to memorize. Pressure drop across choke is a constant enthalpy process. Capital H is constant. Okay? We can use Euler diagram or entropy diagram, HS, or pressure enthalpy chart to do calculation of the temperature drop for Joule-Thomson cooling. Okay. If we need more accuracy, we may need to do some kind of computer software. But in this class, use a chart and show, and there's some equation to do. Okay, let's start. Here is a pressure enthalpy diagram. This axis is pressure in PSI A. This axis is enthalpy or H BTU per pound. It is a lot. I can understand. Right? And if I don't give you an actual paper, we may not be able to read what is what. But okay, zoom in a little bit. There's a line. You see this red line? This one? That is a constant temperature line. Okay, that's a constant temperature line. If I move back, so constant temperature line, T equal to 100, it look like that. So that is constant temperature line. Okay. Constant enthalpy line, just straight line, right? Because this is at a constant enthalpy. Constant pressure line is just like that. Okay. And I have S entropy. I think it's like that, but volume, but we don't really use it. Okay. But we have it, so we don't use that. First example. Okay. We have shown pressure drop from 4,000 to 1,000 psi A, and temperature coming in at 120 Fahrenheit. We have flow through a choke. What will be temperature at the exit? Okay. It is very easy. What you have to memorize it. You draw a straight vertical line, and you get A. Okay. If you draw this line, that's zero. Okay. So it is a constant enthalpy process. First, we have to locate what is inlet condition or before the choke. That is 4,120, right? So I locate it for you. I zoom it in a little bit. I show the line of 120 Fahrenheit, the red one. And from this axis, I can read 4,000 psi. So the initial point is that point. That's the initial point. And I know that after the choke, pressure becomes 1,000. And I need to know that it is constant enthalpy process. H is constant. So I move from that point directly down, okay, and stop at the point where pressure is 1,000 psi. Easy enough, right? So let me repeat. Step 1, locate the inlet pressure, which is 4,000. Step 2, locate the inlet temperature, which is 120, and the temperature line look like this. This S-shaped curve, which is this one. Step 3. Step 3, draw directly downward. Okay. We move from 4,000 to 1,000. And we want to know the temperature after we move down. So we read it from the chart. You see the pink line? The pink line is the S curve shape intersect at the downstream point. I'm sorry, I'm cleaning the screen. Okay. So after I move down vertically, then I try to read what is the temperature at that point. And the temperature at that point is 40 Fahrenheit. So this means if I start from 4,000, I drop to 1,000, the temperature will be 40 Fahrenheit. Okay? And this is for methane. This enthalpy pressure diagram is for methane. If you don't have methane, you have to use other chart. This is 100% methane. Most of the time we don't have 100% methane, right? If we have 100% methane, we don't have to treat it. Okay. We will have something else. So gas gravity may not be equal to the one of methane, but that is for the case of pressure enthalpy chart. Question for me. Or you want question for you? Yes, one question.
So since that's just for methane, will we be...
What do we do from other gas?
Right, where are we going to find the charts for that?
I'll give you. The chart, maybe next time, Mr. Bulat, could you please bring your book, the ATA handbook, to show them where the chart come from. The chart come from American Gas Association handbook. It's very thick and have many charts. Okay, I just take one from that book. In the exam, I'll give you. Okay, you cannot memorize the chart, right? Can you? Cannot. Another way of doing it. Okay, this one is a little bit more empirical. It doesn't do like we didn't use the thermophysical property. We don't directly use the thermodynamic property of the substance. We have the chart for temperature drop, okay, delta T, and we have initial pressure, okay, and we have delta P, which is this line, okay, that's delta P. This one is more empirical and is kind of work for all, and it's give you a good approximation. Let's take a look with this. The previous one is just for methane, right? But if you don't have purely methane, you have something else, we may use this one. Okay? So we have temperature 120 F, right? Inlet pressure 4,000 PSIG. This chart uses PSIG, so I change to PSIG, but PSIA is about the same for very high. So I start from 4,000 PSIG, and I know that outlet pressure will be 1,000. 4,000 minus 1,000 equal to 3,000. Is it 3,000? Okay, 3,000. And this line is 3,000 line. So I move up, reach that point, move to the left, and read the temperature drop. And it's a 80 Fahrenheit. So this means if I have inlet of 120, the temperature will drop by 80 Fahrenheit, it becomes 40, which is the same answer for this case, right? The same answer for this case. There's additional note. This chart gives you this. We need to know how much liquid hydrocarbon content of water that we have. If we have some liquid produced, okay, look at this one. If oil production is 20 barrels per million standard cubic foot, if oil production is 20, it's about 20 barrels per million standard cubic foot, we don't have to do anything. That's it, done. Okay? No correction needed. But if we have more liquid condensed, delta T become less. And we have, it say, okay, If it is 20, the correction is 0. If we have more liquid produced, like 30, we have to do something. Look at this. Look at the case for no oil produced. So if we don't have oil produced, the correction factor is minus 10. Okay. I calculate the delta T, which is 80 Fahrenheit, right? 80 Fahrenheit is answer without correction. Then I do minus 10. Then it becomes the case of, oh, I have to do minus 10 for everything. So I use 120 minus 80, which is 40, right? That's the answer without correction. But if we need correction, we add minus 10, so it becomes 30 Fahrenheit. So this means if we don't produce any liquid phase at all, the temperature will drop more. Okay? If we produce some liquid with it, the temperature will drop less. Yes?
Is it production of liquid in general, or water versus oil, or just total?
Approximate temperature correction for hydrocarbon liquid content of water. I think for this chart it just say liquid in general. But from my point of view, I look at CP. C sub P, which is heat capacity. Heat capacity of water, I just Google, is 4,182 or something. Kilojoule per kilogram. Or joule per gram. That's 4,000. For oil, it's about 1,800 or 2,000 joule per kilogram. For natural gas, it's about that much, or maybe a little bit less. The reason that the temperature drops less when we produce more liquid is like liquid or water has more heat capacity. Okay, so when it have more heat capacity, it can carry more heat with it. Make sense? So when liquid can carry more heat with it, we remove the same amount of energy, the temperature drops less. So this chart is for liquid condensed. I think it's liquid in general. Okay, but it gives a good approximation. Okay, where do I get this? Where is this? Mr. Gula, is that GPSA? GPSA handbook. Okay, and I didn't buy it, but he bought it. It's from that book. Another chart. This one is Euler diagram. Enthalpy entropy chart. For enthalpy entropy chart, this one is entropy BTU per pound mole per degree. Okay. And this is enthalpy BTU per pound mole. I think quiz of last year I asked about unit of enthalpy. Okay, so memorize that just in case if you have that in quiz. But we may not have that in quiz. Okay. So how do we use this chart? The way we use it, we use the same way. We need to, number one, open the right chart. Okay. This is the chart for 0.6 gravity natural gas. If you have 0.8 or 0.7, don't use this chart. But if you have 0.6, use this chart. Okay. Once we open the right chart, we have to know that pressure drop across the choke is constant enthalpy, or we have to move just like that, horizontally. Step number one, we locate the pressure at the inlet. Okay, pressure at the inlet. We have about 4,000, right? So this 2,000 and that 5,000, 4,000 maybe somewhere over there. Step number two, locate the temperature at the inlet. We have 120, right? This is 100, so 120 is about like this line. It's a little bit difficult to look at. But. So this line, let me select one that. Okay, the S shape like this, that is for temperature. The curve like that is for pressure. Step number one, we know that we have to locate the pressure and temperature at the inlet. Let me zoom in. I know that pressure at the inlet is 4,000. Pressure, before the shock is 4,000. After the shock is 1,000. So I locate them and I draw a line. Okay, just follow the line. And then I locate the temperature at the inlet, which is 120. Okay, with 120, I draw another line. The point where 4,000 cross with 120 is this line, this point. So that is upstream condition, okay, before the shock. After the shock, I know that we have constant enthalpy process. Okay, constant enthalpy process. H is constant. So I move to 1,000 psi curve horizontally. So I move just like that. And next step is I read the temperature at the end point. Temperature at the end point is a little S curve like that. It's about 40. Same number that we get before. Do you have a question? No, behind you. You don't have question, but your face looks very doubtful. No question for me? Everyone can do it? What's your name, sir?
Rohan.
Yeah, Rohan.
Can you please repeat the process of reading this chart?
Step number one, locate upstream pressure. Step number two, downstream pressure. So I get this line and that line, right, Rohan? Next, I identify the inlet temperature. My inlet temperature is how much, Rohan? 120. So 120 is about, no, not over there. 100, I have to zoom in to see it. This line is 100, a little bit above is 120. So when 120 cross with 4,000, we get operating point, like that. And we have pressure drop across the shock. Rohan, is that constant what? S or H? We just move horizontally, right? Move to what direction? To the direction that it will meet with the downstream operating line. So downstream line is 1,000 psi, so I have to move to the right hand side. The next step, the last step is we know the point. From that point, we need to follow the S curve and we read the temperature, which is 40. It's a little bit difficult to read for a small chart, but if you have actual chart from PGA handbook, you will get it right. Okay? But we have to open the right chart. We have to calculate the gravity of gas. Okay, which chart already? Graham, Bunting. Graham, if I have more than one component, how do you calculate the average molecular weight and gas gravity? So I have not just C1, I have C1 and C2. What do I do? Oh, let me change question. Did you or anyone teach you about this before? Regardless whether you remember or not. Yes, right? Okay.
Say it again.
Do you remember that someone teach you how to calculate gravity of gas for multi-component? Yes. Do you remember how to do it? No. Who else don't remember how to do it? Okay, we will repeat it. Okay. This happens like this every year. We have to repeat it a little bit. That's what it is. Okay, calculate. Do the short calculation for hydrate. This one is another example, and this one has to do more on heat calculation. Okay. In Silva's textbook, which I think will be uploaded today on the blackboard. It may not be on the blackboard yet. Is it? Silva's textbook. Section 1, it's not section 1, but we have textbook. 1 to 6. We have separator, indirect heater, hydrocarbon, oil filter, blah 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 blah. So the part of the textbook is uploaded already. Okay? For full information, look at that. But for the concise one, just follow the lecture. Okay? It's very difficult to ask you something else other than in the slide and make sure that you can do it. Okay. For this case, I have inlet pressure of 2000 psi, and we need to show to 750 psi. Okay. Gas gravity is 0.7. Flow rate is 3 million standard cubic foot per day. We know the flow rate. Inlet temperature is assumed to be 71 Fahrenheit. Okay. How much heat in BTU per hour is required for this line heater? A little bit more difficult, right? So, for me to know how much heat is required, I need to know what temperature should I heat it up to. Make sense? If I have to heat it very hot, I need more heat. If I don't heat it much, I need less heat. Correct? So let's take a look. In Silva's textbook, we have another kind of chart, which is easier to use. Okay, very easy to use. Okay, step number 1, we identify the gas gravity. The one in this question is 0.7, so we have, if I use U2 chart, you use the chart that have the right specific gravity of gas. Okay, specific gravity. Once we know specific gravity, step number 1, we identify the inlet condition. We have inlet at 2000 psi. So this is the curve between psi and enthalpy. Okay, edge, enthalpy edge. So we start at 2000. So this is the line for 2000. Okay, and we identify the outlet pressure. We need to show to 750. 750 is this dashed line. It's 750. Good. You can identify inlet pressure and outlet pressure and upstream and downstream pressure. Easy enough, right? No question. Okay. Next step is we identify what is the temperature at the inlet. What is the temperature at the inlet? You remember that from previous one? 71. So 71, look at the temperature line. This is 20 Fahrenheit, 40, 20. So temperature line, constant temperature line look like a S curve. Okay. So for this case, 71 is actually on the dashed line. See this dashed line? That is, it keeps changing, okay? Dashed line is not temperature at like 71 all the way. No, dashed line is the curve of hydrate formation. That is the dashed line. That is hydrate formation curve. So this means this chart tells us at what point hydrate will form. And okay, the dashed line says at 2000 hydrate form at 71. Okay, and Silva's textbook assume inlet temperature is at 71. So we have temperature at hydrate formation. It's about to form the hydrate. Okay, that's the inlet. So now we can identify the inlet condition, right? Good. So next step is, what if we don't do any heating and we just flow it through the choke? What will happen? Temperature drop with a constant enthalpy, right? Constant enthalpy. I just move to the right, left hand side. So I just move to that point. That point. So at that point, the temperature is what? Alaina C. Carter. ALAINA Middle name C dot, last name CARTER. What is the temperature if I don't do any heating? Above 20 Fahrenheit or below 20 Fahrenheit? Below 20 Fahrenheit, correct. So that point, I don't know what will it be, but it's something less than 20 Fahrenheit, right? So Alena, less than 20 Fahrenheit, at 750, do I have hydrate? I don't have hydrate. I have hydrate. It's too cold, right? So if I don't do any heating, it's not going to work. So I need to heat it. I know that when I flow through a choke, I just move horizontally to the left, right? So next step, maybe we identify at 750, what is the hydrate formation temperature? At 750, hydrate will form, we have to follow the dashed line. At 750, hydrate will form at what? Do you want me to call the name or you just read it? What's that? 61 degrees, thank you, sir. 61 degrees. So we know that at 750, hydrate will form at 61 degrees. So this means we need to heat it up to a certain temperature, but we make sure that after we cool it down, the temperature will be at least 61 degrees or a little bit more. Make sense? So this means if we know that hydrate will form at 61 degrees or the cross point between the dashed line and 750, we move directly to the right hand side and cross with 2000 line. So that point is the point where we have to heat it up to. The reason is if we heat gas, so initially it's at 71, right? We heat it hotter, and become that point, which is 125. When we choke it, the temperature will drop, but won't drop below the hydrate phase envelope. Okay? Because we just move to the left. So we work the problem backward initially, and we can recheck it later. Good? Question for me. What kind of number do we get? Is that the minimum amount of heat that we should do? Or maximum amount of heat that we should do? It's minimum, right? At least I have to heat that much so that it will just about to form hydrate. If we heat a little bit more, then it will for sure no hydrate form. Okay? But we at least have to heat that much. So now let's take a look on what is heat that much mean. So we go from the enthalpy of 2300 to the value of that point, which is somewhere between 3000 and 3500, and I have it there, 3200. So we increase the enthalpy by 900 BTU per pound. Okay. Enthalpy difference, this comes from the end point that we heat it to. So we heat it to from 2300 until it reached 3200. That is the amount of enthalpy that we have to put in. And the unit is BTU per pound mole. We have to put in 3200 minus 2300, which is 900 BTU per pound mole. Everyone can do this? Yes? Okay. So we have to heat it 900 BTU per pound mole. We have the flow rate of 3 million standard cubic foot per day. We don't have the flow rate of something in the unit of pound mole. I don't tell this much pound mole per day. No, I don't have that unit. So the rest is kind of unit conversion. We can use the chart. Okay. There's another chart It's in the Silver's textbook. It's called heat required for natural gas. The chart will be given for the exam too, but for the homework, you have to locate it. Maybe I may give it to you so that you can do it quick. I flip it. We have enthalpy difference in BTU per power mole on horizontal axis, and we have total heat required BTU per hour on vertical axis. Okay. Previously we know we need 900 BTU per power mole, right? Good. We do the calculation, we need 900. 900 comes from this gap. That gap is 900. And I know that, this is CFD, million standard cubic foot per day. That is 10 million standard cubic foot per day. And here is 3 million standard cubic foot per day. From the problem statement, we have 3 million standard cubic foot per day. So I locate that line, which is this one. I move up from 900 until I reach the point of 3 million standard cubic foot per day, and then I read the value on the side, which is 3 BTU per hour. That is amount of heat required BTU per hour. Okay. Good. So if that heat comes from natural gas, and 1 cubic foot of natural gas gives us about 1000 BTU, do you think it take a lot? Oh, it's not 3. I'm sorry, it's not 3 BTU per hour. It's 300,000 BTU per hour. A lot different. That is 100,000. That is 300,000. So we may need 300 cubic foot of natural gas at least per hour to generate that much heat. Assume we have 100% efficiency from that. Okay. Can you do this in the exam? In the project? Okay. Oh, in the project, I teach about the academic integrity thing, and Mr. Bulat talk about engineering ethics. You have to put it there. Okay, in the project, you have to put the engineering ethics there. Yeah, we will give you a complete list of what to put in, but for sure you have to put something about engineering ethics inside. Okay. So this is about BTU per hour calculation, and I just put here. Okay, from the chart is 300,000 BTU per hour. This is choke calculation with hydrate curve. We may do it without any chart. We may skip this chart. Okay, this chart is just a quick way of doing it. But what if I don't have a chart? Can I just do unit conversion by myself? Yes, I can. How do we do that? So let's take a look. Gas constant is 10.7. Want to restart?